Okay, good afternoon. We'll start, huh? Or we could wait. Instead, we could start. We'll see. We have seen. Okay, we skipped this part, so I thought we'll discuss on this part, and then we'll get into the calculation on the calculation part. That is your all the faults. Okay, the IF value. Okay, their impedance circuit. Okay, the equivalent circuit. We'll see that segment. Okay, from next week. So for this class, we'll be studying about this. Okay. Okay, as we know, during okay, so during fault, okay, due to demagnetizing, okay, effect, okay, so generator stop, okay, this generator stops delivering your active power, okay, stop delivering active power, okay, stop delivering the active power. Okay, this is what we get. So if we have, this is your V and this is your Z, okay, this A, this is B, and over here we have a fault. Okay, we have a fault, that is a ISC, short circuit fault. So not really consider in that particular manner. If we having a short circuit, we could draw into this particular sense, okay, and we could connect over here and we can add as a T, right? Now this is what we know. So active power is stop, okay, while calculating. Now, so when active power is being stopped, okay, so if we consider in this particular segment, okay, so we have V and we have Z. So what will be your V? V would be your ratage voltage of the equipment, right? Where I would be your rated current of the equipment, right? Where we'll have a base, that will be your VB, okay? Where will we have similarly your IB, right? Now, so when VB and IB is there, so Z base would be your V by I. This is one equation we get, that Z base is here, right? Now, Z, what is Z? Z in this is your internal impedance of the equipment, of the equipment, right? Now, so this is what we derive from this. Okay, now active power is stop delivering, right? The active power is not there, there is no picture of that. Okay, now we see that okay, fault impedance, okay, this fault impedance is not included. This point you have to into three phase, okay, fault impedance is not included in three phase, right? So your ISC would be still V by Z. That is your equation 2, what we get, where sorry, Z per unit would be your Z by Z base. Okay, that would be your Z by V by I, right? Then it would be your I by okay. Z would be your I by V by Z. Okay. Now with further, if you see, it will be your I by V by Z. Okay. So therefore, it concludes that Z per unit would be your I by ISC. This is your equation 3. Excuse me. So this is being termed and replaced at this particular segment, right? This I is put over here. Okay, that is being interchanged and it is being done in this manner. Okay, that I would be I by V by Z. So V by Z is your again. Okay, now we'll see. We'll have a note one note that you should have to keep in mind. Okay, that the ratio, okay, of rated current to the short circuit current, okay, gives per unit impedance, okay, of the equipment. It is given that the per unit impedance of the equipment. This is what we get. Okay. Now from this equation we could write that your short circuit current would be your I by Z per unit. Okay. So ISC in per unit could be written as I per unit by Z per unit. Okay. So therefore, I in per unit is always equal to 1. Okay. This is the this part, right? So I in per unit is always equal to 1. So whenever we write ISC in per unit, okay, whenever we write ISC in the per unit, then it will be denoted by 1 by Z per unit. This is the terminology that should be keep in mind. Okay. Okay. Now this is your equation 4, right? That should be noted now. So another to be noted point is for the power system network, okay, the short circuit current, that was your ISC, okay, across the faulted terminal, okay, it's across the faulted terminal can be obtained by taking reciprocal of, okay, can be taken reciprocal of Thevenin's equivalent per unit impedance. Equivalent per unit impedance. Okay, this is the noted point that for the power system network, the short circuit current across the faulted terminal can be obtained by taking the reciprocal of the Thevenin's equivalent per unit circuit, right? So it means that what we have written as earlier in per unit would equals to 1 by ZTH in per unit. This is what it is being stated, and this could be written as the equation 5, right? Now, so in that, your ZTH is Thevenin's equivalent impedance, okay, is your impedance, and Z per unit we know that is your I by ISC. So percentage Z would be your I by ISC into 100, right? We could write this. So your ISC, now ISC could be written as your I by Z percentage. ISC could be written as Z by Z percentage, right? This is your equation number 7, right? Now, so now let's multiply your V both the cycles, right? So we'll get E ISC would equals to VI and Z percentage, okay, right? We'll get this, we'll get this. So it could be denoted your short circuit, right? This is your short circuit. We'll write over here, okay? Okay, this is your short circuit, and this we got as a rated. Okay, as a base KVA. Okay, so we could write the short circuit KVA is equal to, okay, rated or base kVA into 100 by percentage Z. Okay, this is what we get. Okay, this is what we get. Right, if we multiply both the segment, this will be right. Over here would be also 100, right? So short circuit kVA, this is your short circuit kVA by this rated kVA, okay, or base kVA, right? So this implies the short circuit kVA is equal to rated or base kVA into 100 by Z percent, right? This is what we get. We get at last. Okay. Now that if we elaborate that particular segment, okay, ISC would equal to I into 1 by Z per unit would be written as VISC equals to VI 1 by Z per unit. So we could elaborate and we could write V by ISC by V by I is equals to 1 Z per unit, right? This we could write now. So your short circuit power, okay, that is the short circuit power in per unit would be written as 1 by Z per unit would be equal to your ISC by I. Okay, that will be your ISC by 1, that equals to ISC, right? Short circuit power in per unit would be your ISC value, right? Now, okay, because the formula for short circuit current and short circuit power, okay, in per unit part, okay, in per unit, okay, we say 1 by Z per unit, okay, therefore if the short circuit, okay, so therefore if your short circuit, okay, if the short circuit current, okay, the short circuit current is your X per unit, okay, then power, okay, the short circuit power would also be equals to X per unit. This is what we see, okay, this is what we see and this is how we see. Now procedure for symmetrical fault analysis. Okay, this thing we have to remind. So we'll go with step one. What will be your step one? Okay, now by choosing appropriate base values, okay, or we could convert the given single line diagram power system network into power equivalent, your per unit uh, equivalent reactance diagram, okay, we have to convert. Okay, now so first step is by choosing, right, by choosing appropriate base value, okay, now convert the given single line from power system network into per unit equivalent reactance diagram. Okay, so whatever the single line diagram of a power system would be given, you have to convert into per unit equivalent reactance diagram. So for converting that any value into per unit reactance equivalent reactance diagram, you have to choose appropriate value to convert that the nominal value into this. Okay, now step 2. What will be step 2? Step 2 would be identification of buses. So identity. So identify the bus. Okay, so for finding the bus, you have to find which will be your base bus and what will be your rated bus. Okay, you have to identify these two particular segments. Now step 3. What will be your step 3? Step 3, okay, on selecting of appropriate base value is done and selection of identification of buses are done. Okay, so the third value would be okay. So what will be the when the identification of bus is done? Okay, where the fault has been occurred. Okay, identify the bus terminals, okay, where fault is occurring. Okay, now third is to reduce the network into the Thevenin's equivalent circuit. Okay, this is the thing we have to do, right? Now means it will be your VTH, it will be your ZTH, this will be your fault. Okay, this is your fault and this is your ZPB, right? Where VTH equals to 1 per unit, always 1 per unit, and this is ZTH, right? Now, so in this ISC in per unit would be 1 by ZTH in per unit, right? That would also be equal to your short circuit power, okay, in per unit. Okay, this is what will know, right? So it could be written in a very nice way that short circuit kVA would equal to short circuit power, okay, in per unit into common base. That would be kVA, right? This is what we could analyze and we could write. Okay, now we'll see one problem regarding this solving. Okay, so let's need 100 kVA equipment is given whose has 5 percent impedance. Okay, this is the circuit. So what we have to find short circuit kVA value. Okay, this is what we have to find, right? Now, so what it has been given, you have given the 0.055%. Okay, impedance is given. This is your right. This is your circuit viewer. It is now. So what do we know? Just we have seen one formula that ISC in per unit is equal to Y by Z per unit, right? So it will be 1 by 0.05, right? So that would be equals to 20 per unit. That is your ISC in per unit, right? This is what we know, right? Now, so this short circuit kVA in per unit is equal to ISC in per unit that we are going to see. So what will be this value? This would be a 20 per unit. So short circuit kVA in per unit would be a 20 VA, right? So the short circuit uh, kVA value. Okay, short circuit kVA value is your short circuit kVA in per unit into common base. Just we have seen this segment, so it will be a into kVA. So we know this value. This value is known. That is your 20. That is your 20. And common base is your 100. Okay, so it will be your kVA. So what will be the value? It will be your 123 kVA. What is this? It is your short circuit kVA value, right? Now, so in earlier figure I have taken CB, right? So CB, so because regarding this only, so what it say that circuit breaker, we could assume the circuit breaker, okay, should have 2000 kVA breaking capacity. Okay, this is what it should be. It should have this breaking capacity. Okay, we'll see. First is your to limit short circuit current. How we could limit the short circuit current? So first mode part is what we do not consider. We do not consider resistance. Okay, resistance is not considered. Okay, why it is not considered? What will be the disadvantage of this? The disadvantage of this would be your continuous power losses. Okay, so if resistance are being reduced, there would be a consistent power. Okay, this is your 5%, and there would be a power losses. Okay, over here. So this is a disadvantage. That is why resistance has been not considered. Okay, now second is your uh, series capacitance. Okay, series capacitance or capacitor. series capacitor is not considered. Okay, this is also one thing. Means this is your this particular is not considered. Okay, this is not considered. Now why it is not considered? The main is your disadvantage. Okay, why it is being not considered? Okay, now we'll see about this. It is not being considered. Okay, no, so we know V equals to I XC in normal condition. Okay, under normal condition, this is what we know. Now second is your under short circuit condition. What will be this? This will be your ISC. Okay, right? So now when it is this, so VSC would equal to ISC into XC, right? Right, this will be there. So during short circuit, okay, this short circuit condition, voltage drop is very high. Okay, voltage drop is high due to short circuit current. Okay, during short circuit condition, voltage drop is high due to short circuit current, which is several times larger than the rated current. Okay, this your ISC would equal more than I, and VSC is also more than V, right? So during this condition, okay, there's during a short circuit condition. Okay, during this particular okay condition, your voltage drop is very high. Means the short circuit voltage is very high due to the ISC current. ISC current is there. Okay, now which is several times larger than the rated current, that is your I, right? So we have to provide heavy insulation, which is very costly and expensive for it, precaution or prevention. Okay, this is why this is not in. Okay, heavy insulation is the cost will be increased, and this is for this rated of insulating and prevention. This that is very uh, high. Okay, now so during short circuit condition, heavy voltage drop across capacitor also damages your insulation. So this is what we get. Okay, we get the point is during short circuit okay condition, heavy voltage drop across the capacitor damages insulation. Okay, this is why we do not go for series capacitance. Okay, now third is your series reactor are used to limit ISC, that is your short circuit current, to limit short circuit current. Okay, this is your 5% and this is your XC. So we do not use resistance, we do not use series capacitor, but we use series reactance. Okay, now what will be the advantage? Why we use? Advantage of using this is no power loss. Okay, second is no insulation. breakdown problem. Okay, so these two things are being given. Okay, now why so we'll see. First is your inductor. We know one inductor is linear. Okay, inductor is linear until the saturation. Okay, it is linear until the saturation. So we know L equals to N 5 by I. Okay, so if I is increased, phi is increased, your L would be constant. Okay, when I is decreased, phi is decreased, again your L is constant. So there is no change in this. So okay, it is there that saturation problem, that is L is decrease, I is increase. Okay, after some time, okay, it means it will burn out. Okay, now so resistor is linear if temperature remains constant. This is one. Capacitor is linear until the breakdown of insulators take place. So because of this, we choose this segment. For R and for C, there is the thing, if temperature is remain constant and will be linear. Okay, and capacitor is linear until there is a breakdown. But you know there is due to short circuit, there will heavy voltage drop at C, and there will be the chances of breakdown of that. So because of that, we do not consider, right? Sure. So that what the part what we were able to see. Now we will be, time is going to end, and only few seconds are there. We will be ending over here. Okay, we'll see in next particular class. Okay, see ya.